Good morning. Today we are going to deal with nuclear fusion. So what is nuclear fusion? It's a phenomenon of two or more lighter nuclei to form a heavy nucleus. Two or more lighter nuclei combine to form a single heavy nucleus. So why the nucleus undergo fusion reaction? We know that we had studied it in the binding energy curve. For the nuclei with a low mass number, in order to attain maximum stability, it has to increase its mass number so that it can reach the region of greatest stability, that is near iron. So in order to have more mass number, the lower nuclei or lighter nuclei will combine to form heavier nuclei, and that process is called nuclear fusion, and the nuclei undergo nuclear fusion in order to attain stability. Now the mass of the product nucleus is less than the sum of the masses of lighter nuclei which are fusing together. And we know that difference in mass is known as mass defect, and the energy equivalent to that mass defect is known as binding energy, which is released as the energy in the fusion process by the equation E is equal to delta M into C square. So energy released in a fusion process is given by delta M into C square. So this is a example for nuclear fusion reaction in which a deuterium and tritium fuse together to form a helium nucleus along with a byproduct of a neutron and a huge amount of energy. Now, what are the conditions under which a nuclear fusion can take place? So this nuclear fusion takes place under the condition of very high temperature, that is approximately 10 raised to 7 K, and very high pressure. Why this condition is necessary? We know that fusion is a process of combining two or more nucleus, isn't it? And nucleus are having positive charges. So when they try to combine together, what happens? The Coulombic repulsive force will try to move them apart. So the protons have enough kinetic energy and they can come closer than the range of the nuclear forces against the electrostatic repulsion. So proton should have the enough kinetic energy to come closer. So in order to get that enough kinetic energy, we are providing high temperature and high pressure. Also higher density is also desirable, so that the collision between the nucleus occur frequently. So three conditions are there: high temperature, so that high pressure, and high density, so that the protons will have enough kinetic energy to come closer and fuse together. And these conditions can be seen or are met within the interior of Sun only, and it cannot be arranged easily in laboratory. Already said high temperature means 10 raised to 7 Kelvin, isn't it? So the temperature, high pressure, and also high density cannot be arranged easily in laboratory. In the last class we had studied fission reaction. Now just we are going to compare the fission and fusion reactions. So what is the energy released in one fission reaction? It is 200 MeV. which is very high. But the energy released in one fusion reaction is very small when compared with the fission. It's only 24 MeV energy is released in one fusion reaction. But the energy released per unit mass, that means that energy released has to be divided with mass. It is high in the case of fusion than fission. See, in the case of fission, we are dividing 200 MeV divided by 200 MeV is the energy released in a fission process, and there the nucleus was uranium-235, isn't it? So 200 MeV divided by 235 U is only 0.85 MeV per U, that is energy released per unit mass. It is low in the case of fission reaction. But in the case of fusion reaction, we have energy released is 24 MeV. Per unit mass means it's divided with 4U. So 24 MeV divided by 4U. We know that 4U is He24, isn't it? So divided with 4U gives you 6 MeV per U. So on comparing with the fission reaction, we can see that the energy released per unit mass is high in the case of a fusion reaction. Now what about the products after these reactions? After fusion, the products are safe, but the fission products are radioactive. That means they can harm. So the fission products are radioactive. Now we already studied about nuclear reactor that undergo a nuclear fission reaction, isn't it? So controllable fission reaction is a reality which we are using in a nuclear reactor. But controllable fusion reactor is not a reality, since we need a high temperature, pressure as well as high density for fusion to occur. So these are the 4 important points regarding fission as well as fusion reaction. It's a picture showing the fission reaction as well as a fusion reaction. Fission, in which heavy nucleus is split into lighter nuclei, and fusion reaction, smaller nuclei combine to form a heavier nuclei. Now what is a thermonuclear reaction? We know that for fusion, positively charged nuclei have to come close, isn't it? 2 or more lighter nuclei are coming together to form a heavy nucleus. So that means positively charged nuclei have to come close. So when positively charged nuclei come closer, what happens? There is an electrostatic force of repulsion. So in order to avoid that repulsion, more energy is required. So high energy is required to overcome the strong electrostatic repulsion between the positively charged nuclei. So for that we are raising the temperature. So by increasing the temperature to about 10 raised to 8 Kelvin, we can make the positively charged nuclei together. And how we are raising the temperature? With the help of a fission process. So such a high temperature can be produced by inducing a fission process. So that a fusion process is also known as thermonuclear reaction. Once again, in order to overcome the strong electrostatic repulsive force between the nuclei, more energy is needed, and that energy is obtained by increasing the temperature by inducing a fission event. Therefore, a fusion reaction is called thermonuclear reaction, which is the basic hydrogen bomb. So hydrogen, in the case of a hydrogen bomb, you can see that a fission process takes place first and after that a fusion. With the help of raising the temperature, hydrogen bomb is working on the principle of high temperature. So picture showing the nuclear fusion reaction in stars. No need to study, just for looking the several layered structure inside a star. And we have to know what is a solar constant. What is solar constant? By the name it's related with the sun, isn't it? So we are receiving energy from the sun. So energy received by the earth in every second by a unit area is called solar constant. So it is an energy received in every second from the sun by an area of 1 meter square. So the total energy is approximately 4 into 10 raised to 26 joules, or we can say that it is energy radiated by sun per second is 4 into 10 raised to 26 watt. How can we calculate it? It is 4 pi r square into 1400. So 4 pi r square is the area, overall area, having radius r is equal to 1.5 into 10 raised to 11 meter. That is the distance between sun and earth. No need for calculation. You just know what is the solar constant and what is the energy radiated by the sun per second. That is 4 into 10 raised to 26 watt. So the sun has been emitting this much amount of energy, high amount of energy. Now what is the source of energy of sun? That is a process called nuclear fusion. So nuclear fusion is the main source of energy of sun and stars, because in the interior of the sun and the stars where extremely high temperature exists, conditions are very right for the fusion process to take place. That means fusion of hydrogen nucleus into helium. So that large amount of energy is released and which sustains the sun and the stars. And the process of fusion of a hydrogen nuclei to form a helium nucleus, which is known as a fusion reaction. It will take place either by proton-proton cycle or through carbon cycle. So this is the fusion reaction that takes place inside a sun and stars where there is higher temperatures and high pressures are there. See here H11 plus H11 giving you H12 plus electron plus its neutrino. Again H12, that is a product of first reaction, combines with another H, that is H12 plus H11 gives you He23 plus gamma. See, after these two reactions you will get an He23 and again this reaction takes place and He23 is producing more and more. Now 2 He23 combines and forms He24 plus H11 plus H11. So this is a proton-proton cycle in which Initially, two protons combine to form a deuterium nucleus H12 and it's not an electron, it's a positron. A third proton which combines with deuterium nucleus to form a He23 nucleus. Finally, two He23 nucleus combine to form He24 nucleus and produces two protons also. And the total energy evolved in this process is 24.7 MeV. We had already said that what is energy released in a fusion process is approximately 24 MeV. This is a proton-proton cycle, and why it is known as proton-proton cycle? The first reaction, the first reaction includes the combination of two protons, H11 plus H11. So the energy released in this process is 24.7 MeV. Also the energy released per unit mass is 6.2 MeV. So this is a proton-proton cycle which occurs inside the sun and star that contains, or in the process there is a fusion of 4 hydrogen nuclei. See, here you can see 4 hydrogen nuclei and they combine to form a helium nucleus He24. So that is a nuclear fusion reaction that takes place inside the sun and stars. So process of nuclear fusions are the main sources of energy in sun and stars, and this hydrogen process in which the hydrogen nuclei combine together to form a helium nuclei will take place either by proton-proton cycle or by carbon cycle. Thank you.